and we're starting here with Florian. Are you ready?
Yes, I'm here. That's right. If you could just briefly confirm if you see my slides.
Not yet.
Okay.
It sounds like it's coming. Yep.
Yep. Okay. Wonderful.
Okay.
Great. So welcome everyone. I'm very happy to be here. My name is Florian Geisler. I'm with Intel Labs, a group in Germany, and I'm excited to present you some work that we did together with our colleagues at the University of British Columbia, where we try to go towards a safety verification approach of CNNs in the presence of hardware faults. So let's get right into
Florian, we are watching your view rather than the presentation view.
Yeah.
Oh, okay.
Showing the presenter view rather than the audience view.
I see. Sorry for that. Maybe now.
This is better.
Okay, great. Sorry for that. All right. So what are we talking about when we say platform faults here? So platform faults can be a variety of things. So whenever you run a DNN on a specific hardware implementation, there's always a chance that the underlying hardware platform has a specific error that impacts the performance of the deep neural network on an application layer. And this can be due to many different things. So we can have, for example, permanent or transient faults. We can have very different faults, root causes. So for example, that can be faults already in the production process, design errors, aging, or internal and external electromagnetic disturbances on the circuitry. And so there was an example of the Blue Water supercomputer in Champaign, and they found that if they run very high workloads for a long time, hardware faults were actually the major cause of failures here. So we want to make sure that this doesn't affect a safety critical application of a DNN. A couple of studies have made this connection where they identified how DNNs can be disturbed by platform faults. And we'd like to focus here on a specific connection between soft errors and platform faults. So soft errors are typically transient faults, and they're due to either electromagnetic leakage on the chip or due to external radiation of neutrons, for example. We can model those most commonly as bit flips in memory elements. And if the memory element holds a value that is relevant for the neural network, for example, a learned weight parameter, then we will get an error. And we talk here about silent data corruption because we have incorrect behavior which is not signaled in any way. So we would like to avoid that such silent data corruption events affect the safety of our DNN application. An example would be the following. Here we have an automated driving vehicle which classifies the objects in its environment. And maybe due to some transient soft error, you get a bird instead of a truck. And this is obviously safety critical because you might react in a very different way. What can we do about it on an application level? So unfortunately, even the best hardware platform errors are not fully avoidable. So we want to mitigate it at the application layer. And the method that we pursue here is range supervision. So what does that mean? We check the intermediate activations of the network. The underlying assumption here is the following. So if we have a bit flip that creates a very large value, this value gets even larger if it propagates through the network. And eventually we end up with enormously large values that are very different from the expected value range. And this leads then to STC and mispredictions. So that's why we insert these protection layers in between critical layers of the network. And these layers, they do nothing else but just to bring back abnormally large values to reasonably large values. And of course, the question is, what is reasonably large? So we need to extract some kind of expected thresholds beforehand with an independent test data set. And this mitigation strategy was here presented already by our colleagues. What is novel here is that we try to find new mitigation techniques that are more true to the original feature map topology of the network to mitigate faults better. We also consider a broader spectrum of faults, so not only in the activation values itself, but also in the learned weight parameters of the network. And most importantly, we want to use this strategy to build something like a prototypical safety case to quantify safety for a CNN, or at least try to go towards that goal. So what is a safety case or a safety argument? Well, it's a formal way to verify that a specific safety goal is reached. So we would just come up with the following goal. The system should be sufficiently safe in the presence of the platform soft errors. We need to make a lot of boundary condition assumptions here, of course. So what is our fault model? What is the operational design domain, and so on. And then what we would do is to split this goal into sub-goals that we can quantify. So in particular here, we follow a probabilistic perspective. So we would start from the definition of risk and say, how can we make sure that we have an efficient error detection, mitigation, as well as we want to make sure that the severity of an error is not increased by whatever modifications we do to the network. Obviously, this last part can only be specified in a specific use case context, because the severity depends very much on the intended use of the function. And eventually, we would like to go towards a safety case that gives us a specific compliance with safety standards, so such as these ACL D levels for automated cars, but not for a mechanical component, but for a AI component here in this case. Okay, so I'd like now to go through the detection, mitigation, and the severity aspect of the safety argument. Here's an example of what range supervision really is doing. So it's a simple example of the LUNET 5 network and MNIST dataset. To the left, you see how this input image is passed through the network, and you can see the feature maps visualized as activation magnitudes here. And we extract the features on different levels of granularity and get a prediction of a 0 at the end. Now, if we inject a fault in a specific kernel of the convolution layer, we get, in this case, very large values here, as you can see. And these very large values, they propagate through the network, and they affect more and more parts of the network. And in the end, we get a completely wrong prediction. And what range supervision now is doing, it contains these incorrect values, as you can see in the third column. So you cannot perfectly restore the original topology, but you would just make it small enough so that the subsequent propagation of the fault is not detrimental anymore. And you can see, indeed, in this example, we get, again, the correct prediction. So now we have explored and studied more fault mitigation techniques that go beyond the mere truncation of the value, but also try to restore the topology of the feature map more accurately. So we call these methods here clipping, rescaling, backflip, and feature map. The idea is in rescaling, for example, we do a linear mapping to the expected value range. Backflip tries to undo specific bit flips that we can reason about. And the feature map average tries to use neighboring healthy feature maps to restore a corrupted feature map. And you can see here in this visualization that we can get kind of close to the original fault-free case. We have done, of course, a lot of fault injection experiments to scale that up. So first, in terms of detection, how can we quantify the detection? Well, we would measure how many of these protection layers get activated in each run. And that happens if a fault is large enough to exceed the specific bound. And we get precision recall values that are very high in this case, so of the order of 99% and more. So what it means is that all the fault cases that eventually lead to silent data corruption, they were large enough values to be detected by these ranger layers. So this is a very good error detector here. And second, in terms of mitigation, we can see the suppression of the SDC rate from original values that are of the order of, let's say, 10% in the classifier networks, ResNet 50, VGG16, and AlexNet, and one fault, to values that are almost zero for the mitigation techniques of Clipper, Backflip, and feature map average. And if we go to 10 faults, then you can see that the fault-free cases, the unprotected cases, roughly 50% and more SDC. So it really makes a big difference here that we add this protection. And finally, the severity. So here we have put this system in a specific context. We used the MyoVision dataset, which contains traffic camera images for object classification. And we have selected this use case that we have a safety impact if we have class confusions that are particularly critical for somebody who would navigate based on this data. So we have divided the classes that this MyoVision dataset provides into 3 clusters, which would be the vulnerable road user cluster, the non-vulnerable road user cluster, and the background. And whenever we have a confusion from a more vulnerable to a less vulnerable class, we consider this confusion as particularly safety critical, because you would interact in a less cautious way with this object. And in this simplified risk model, we can quantify how many class confusions are critical or non-critical and how they get mitigated with the protection method that I described. And we see that indeed the safety critical and the non-critical cases, they get proportionally suppressed, which means that the protection that we add does not increase the severity of an error. So it keeps it either on a similar level or even reduces it. So meaning that we do not expect any particular risks due to our modifications. And I think I have to come to the end already. So let me just recap real quickly. We have started from the idea that platform faults are a threat to DNNs running on this hardware. So we seek to mitigate it on an application level. We use this range restriction approach to detect and mitigate these errors, and we can see that this is highly efficient in the selected use cases, given specific data precision, fault model, and so on. And eventually, you want to use this to build a safety case and to provide evidence to the goals that we define in our safety argument. Of course, that's not enough time to really go into any details, so please check out our full paper if you're interested, or just drop me an email.
Thanks, Florian. You're running a bit behind. Please, let's switch to Beatrice. Are you going to present?
Yes, please. But I think Florian should switch off.
Yeah, relinquish control.
I'm not able to share.
Oh.
So you can do it. Okay, thank you. Now I shall share my screen now. I hope you see it.
It's not coming yet.
No. It worked before.
Okay. Is this okay for me?
No, not now. No, it did work before, I know, because we tried it.
It looks for me that I share my screen.
Mm.
Huáscar started screen sharing.
Yeah.
Oh,
Oh, there you are.
Thanks.
okay. Thank you, Huáscar. So, okay, so we saw several examples today about safety critical applications for autonomous driving. I would like to talk to you about another safety critical application, which is in the skies, so avionics. This is a position paper, actually. We'd like to show the progress in the ongoing standardization activities in the framework of certification and approval for aeronautical products. Next slide, please. Thank you. So this, well, Umut mentioned it. This is a joint effort between ECSEL and SAE. And it already gathers together more than 500 engineers around the world, representing main components, system manufacturers, and also UAS manufacturers, but also the regulators and the authorities, NSPs, and so on. And well, I'd like to thank all the contributors for their contribution to the standard. And the house you see on the right-hand side represents the way this group works and what it was its first aim. The first aim was to actually agree upon a number of concerns across the industry and also the taxonomies that needs to come across from the different fields. And this was discussed and it was settled together with a number of use cases in the avionics industry. So these are the foundations, the use cases, the taxonomy, and also the concerns. This structures the entire work. So the main output of the standard will be the two main applications, airborne and ground. And probably this will lead to slightly different documents, as it was the case in the past also for the avionics standards. But on top of this, we see also the working group organization, which is structured along several subgroups and has a common leadership from SAE and ECSEL in order to have a common standard at the end. Next slide, please. So you see here how the future standard will come into the picture when it comes to the insertion and the interfaces with the other standards. So for the, let's say, classical software development, you know, the system level standards, the model level standards, and the item components. And every time you have, as I said, slightly different documents for airborne and for the ground. So when we talk about the insertion of machine learning models and software into the avionics, we see this at the level of the model standard, and the interface will be done with the classical standard, so which will not be affected. But we need to be very clear and very careful about the interfaces. Next slide, please. So, several challenges come, as you know, with the neural networks, and I would like to say that indeed we limited for the moment the scope of the standard to machine learning and to the offline learning. And still for this, the challenges are numerous related to the black box aspect and the fact that the requirements need to be defined in different ways from the classical. And this is also related to the fact that the data came into definition of the requirements and the validation and verification of this. And of course, this is related to the data representativity and completeness, which are completely new challenges for the standardization. But another main challenge we derive from the previous one is related to the robustness and to the verification of the model, of the machine learning model. Because of course, we need to evaluate the robustness of the algorithm with respect to the changing in the training set. So this is indeed something new, is that you will have a different system every time you train with different data, which is a new topic, and we need to evaluate all the safety challenges that are raised by this. But also we need to detect unintended and unexpected behavior of the neural networks. And this is also related, as we discussed with Umut, with some corner cases, corner data that we should input to the neural network to be sure that in addition to the real data sets, we can ensure that the behavior is correct and unharmful for any other inputs. But also we need to evaluate the robustness of a trained algorithm with respect to different data and to the adversarial inputs in particular. And also we need to assess the intrinsic robustness of these models through formal or empirical methods. So these need to be defined, and we need to give the means to make this assessment. And then another aim would be to have an assessment of the methodologies that can guarantee the enhancement of the robustness. Last but not least, there is, of course, a trade-off between performance and robustness for all these models, and we should be aware in the standard about the requirements that we ask in order to ensure both of these axes of evaluation of performances for a model and not only one, of course. And last but not least, when everything else intrinsic to the neural networks have been checked and failed actually. And here I come to the presentation by Simon. We need to have a holistic view and to define all the safety mitigation aspects in order to ensure the safe functioning of the network. Next, please. Next slide. Okay, thank you. So this is the organization in subgroups, and you see that there are several subgroups dealing with all the issues that I mentioned, and in particular, the subgroup 3, which defines the ML life cycle that I will discuss in the next slide, please. Next. Okay, so the machine learning life cycle actually is a new concept that was defined, and we said that it should be very generic in order to apply this to all the technologies that can come, but also process and environment agnostic, and should be coherent with ensuring assurance objectives that should be defined by the regulation authorities. Next slide, please. That I will skip because it's very long, but you will find a lot of details in the paper. And this is actually what are the outcomes of the standard will give. So first of all, already you have the document with the statement of concerns. And in the next slide, you see the roadmap of the standard, which is perfectly aligned with the roadmap of EASA that Umut also has presented previously. And you see that for this first version, you will have actually an issue in beginning 2023, and 2 years later will enhance to other AI technologies. So not only offline learning, probably adaptive learning, and more open technologies for AI. Okay, so thank you for your attention, and let's discuss more details during the panel.
Thanks, Beatrice. Great portion of the session, where maybe we'll open the floor for questions. And if people want to raise their hand, I see John. John, you have your, do you have a question?
Yeah, sure. Mauricio, thanks. I have a few, but maybe if I ask one first and then give a chance for others to chip in, and if we've time, I'll come back. So perhaps if I can turn just to the last talk, Michael. It won't surprise you that I think the idea of doing assurance cases is very attractive. ALAP is very tricky. To apply ALAP properly, it requires you to compare alternative designs, but also you normally apply ALAP at the level of hazard risks rather than at phases of the life cycle. So I wonder if you could give us some views on actually how trying to apply ALAP at the level of phases of the life cycle really allows you to talk about hazard-related risk, and if in the process you propose, you actually look at different alternatives, because ALAP does require you to say, actually, I've looked at different designs and none of them do better than this. And that's actually, in practice, that's quite tricky to do. So sorry, a tough question, Michael, but hopefully you've got some insights.
Let me try to answer this in this way. Clearly, we need to make some simplification in the way that we say, okay, we do our best in each case, and this sums up to be the best overall. For sure, this is maybe not the truth in general, but it's maybe an assumption you have to make. And then the idea is that you let's say you use this kind of saturation you have typically if you dealing with ML, so that you say, okay, I do stuff. For example, I'm using additional data, and somewhere I see that the cost of using more data if I monitor my process maybe is not that cost effective anymore, so that I have a certain point where I stop. This is the core idea. We have also a picture on this in the paper. I have no time to present, but for sure it's a kind of a simplification. But I think we require this to have at least some way to argue. And also, if you have, for example, different alternatives for the design of your model, then you may take the three that are the most promising, and if you see that they are comparable in their performance, then do not check additional ones. But if you see that they are largely different, then maybe you take two additional and check whether you find some better alternatives. So that's what our interpretation of the ALAP principle in this context.
Okay, thanks. No, I mean, certainly what you're saying there about comparing models makes a great deal of sense. I just wish people did that rather more often. But anyway, thank you. That's an interesting answer. So Mauricio, back to you. But I've got some other questions if nobody else has.
Yeah. I mean, we do have questions. I see Huáscar has a raised hand, and we'll go with Florian.
Yeah. Okay. Yes. A question for Florian, actually. I like very much your presentation. I think your approach could be a good idea to present it to Tesla, who presented yesterday their Dojo chip, and they didn't talk anything about safety in all their AISafety AI day, I think, at Tesla. But this is a very interesting topic. So I saw that both presentation 1 and 3 are very related to the safety case or the assurance case. This is very nice, but I don't have, while for the Michael presentation was clear for me what is the focus and the connection between this assurance case and the risk assessment process. It's not fully clear for me, your work, what is actually the focus, either we can say, the assurance case engineering process, or more to try to provide a complete set of arguments or evidence to provide this hardware platform are safe. So I'd like to go to the safety engineering point of view, if you work a little bit on that. But since you're in Intel, maybe you already did, you need to provide this hardware process to other system level or subsystem level providers. So have you thought about how you could articulate this safety case or this assurance case you are building with a system level assurance case? I mean, if, for instance, some user of your components wants to use like a certification package, all this information, have you identified what are the interfaces, for instance, what are the parameters that you need to provide? I mean, in terms of assurance case to the user of your hardware, in order to enable the higher system level assurance case. Have you thought a little bit about that?
Right. So first, thanks very much for the nice assessment. So yeah, I think there are two key points here that I would like to address. So first, the safety case that we are approaching, let's say, is by far not complete, as Michael explained very well. We're just looking at a subset that is relevant here for us. But the idea always has to be that we're taking a small piece of a more complex safety argument. We try to find evidence for that, and then ideally we would plug that back into something bigger. So we would use that as a modular building block for a more complex safety case. So we tried here to cover the detection and mitigation with respect to a specific platform fault type. And I think we can quantify that in some respects, but there has to be something around it, of course, to go to a system level, as you say. And I think the interfaces that you were asking about, so yes, there are many. So first of all, I think it really depends on the use case. We have restricted ourselves now to classifier networks, which are as such not yet an autonomous car. It's part of a perception pipeline that involves classification, but you would have to do similar things for the localization of objects and for maybe the actuation and all that. So I think there are many interfaces in that respect. And since you were also asking about the hardware specifics, so yes, we have at Intel, of course, many colleagues who are looking into hardware fault models, and it can be arbitrarily complex to really try to drill into the exact trace of a fault that somehow occurs in the memory up to the application level. So we found that just a more pragmatic approach is to go with the memory bit flips that we inject directly in the network in simulation. And this is a bit like a worst case scenario. So in practice, a hardware fault would probably not exactly look like that, but it would be less detrimental actually. So because you're just affecting maybe individual operations and not the whole memory value. Also, you can have something like ECC or parity protection in some elements. So we're kind of looking at the worst case here, and our approach is to start from there and try to refine. For sure, there are many more things to be explored from here.
Okay, great, thank you.
And Florian, you had your hand raised before. Did you want to ask someone?
Right. So if I may, I will have a question to Michael. You mentioned as one of the safety quantification metrics, you mentioned this neuron coverage. So I was just curious if you could comment a bit on that. Do you mean neuron coverage in the sense that you try to evaluate all possible outcomes of the network prediction, Maybe you can comment on that a bit.
Let's say the topic of neuron coverage, it's a little broad, so there are different definitions of what neuron coverage is. In general, the idea behind it is that you, let's say, activate each neuron in the network for a certain extent, so that your, let's say, test data set cover, let's say, the activation of each neuron. So that the whole network is tested in some way, such as, let's say, statement coverage, if you think about testing. How much this is related now to how good your model is in the end, or how risky, this is an open question, at least for me. But yeah, this is something that is proposed, and to a certain extent maybe meaningful to be considered. But I would not rely only on this, or let's say this is if I have to reach this coverage of this percent using this concrete neuron coverage criteria or measure, then I be that and that safe, or I have this and this fault rate for my model.
Okay.
Yeah. Okay. Maybe John, I think you have another question.
Yeah, thanks, Mauricio. Actually, just on that last point, there are some papers that suggest that neuron coverage isn't a great metric. But if I could come back to Florian, I think very interesting talk. I think it's really encouraging to hear people thinking about the hardware issues underlying this as well. So thanks very much for that. I understood why you focused on severity as an issue. But I think there's a broader issue of risk, and I'd be interested in your comments on that, because these functions that you're adding might change the false positive versus false negative ratio, so they might actually change the probability of some of the other outputs. And actually, in an extreme case, the restrictions by these range gates might actually change the hazard type. And I know of at least one case on a pre-ML system where because of a range limiter like that, a different hazard arose. So as it's a rather discursive point, but I'd just be interested why you did focus just on severity and didn't look at this broader issue of risk, or if that's the next step maybe.
Right. Yeah, that's you're totally right, John. So we have built our prototypical safety case around a more generic definition of risk, which would be the probability that something is happening times the severity that event causes. But as you again emphasized, the severity is as well a complex term in itself, and the hazard that a specific event poses to a user depends, of course, very much on the function that is implemented and what's really the prediction of the neural network is going to be used for. So if you have, for example, a car just being parked on the curbside, you wouldn't really care if you miss all the objects around you, because you're not going to do anything. Sure. But on the other hand, whenever you drive, you really want to know what's ahead of you. So that's why we had to restrict ourselves here to a specific examples to quantify severity in this case. But I agree, there's more complexity to that, and we might want to go into other scenarios to really come to a more realistic notion of severity.
Yeah. Sure, thanks. So I think it's a great step forward, and maybe sometime we can have a discussion. I can explain to you a couple of problems I know that occurred where fault limiters have actually given rise to a different hazard than the one they were trying to mitigate. And maybe if I explain that, that might give you some stimulus for other things we might look at. But thanks. I mean, so again, I'm really pleased to see you addressing this. So many people ignore the hardware issues. So that's really great. Thanks.
Beatrice?
Yeah, I just wanted to say that indeed, maybe in the slide that I skipped, we actually are coming to the same conclusions. So actually we are looking at, during the life cycle of the machine learning model, we are looking at all the stages where it's possible to inject faults. And then actually we identify from this the assurance objectives, but also we try to identify the potential sources of errors, and together with them, well, not the severity, but to evaluate the worst credible effect actually onto the machine learning models. So actually, this study of the worst credible effect on the ML model and the study of the failure modes are very important in the standard we develop in order to ensure the safety and the assurance objectives. So it's very close actually in the approach with the autonomous driving standards and works that are done. And I think it would be worth establishing a liaison with the other standards presented also, the ISO presented by Simon, and I think we should keep in touch for further liaisons.
Thanks, Beatrice. Simon actually has a question.
Yeah, thanks, Maurizio. Yeah, and thanks, Beatrice. It's very interesting to hear your talk about standards, and I really do think there needs to be more cross industry collaboration on standards as well. I wanted to ask maybe a controversial or maybe very open question to the speakers, to pick up on something that Michael said about, using the alert principle. We would sort of reach an asymptote of how good we can get a performance, and without wanting to scare people, I'd just like to ask the speakers their opinion on whether the performance of AI using the types of techniques we're currently talking about, deep neural networks, etc., will it ever be good enough for a safety critical system for typical perception tasks like we've been talking about today? So any opinions there? Or will we reach an asymptote which is just going to be orders of magnitude not good enough for safety?
Maybe I'm starting. I see that we never will reach reasonably in the next time some 99.9 something like that which is required with regard to hardware failure. However, on the other side, we can also think about that AI is integrated in the system, and finally from the system comes the requirements to the AI, how good it has to be. And maybe I have enough, let's say, safety measures integrated in my system so that the AI has not to be that strength with regard to requirements, so that maybe 99 or 999 is sufficient for us, and maybe this is achievable in the next years. So this would be my opinion.
I've just got a quick reaction to that, and I just want to, it's Friday evening my time, I just want to provoke some things. So if we were to say, let's say 90%, yeah, mean average precision or whatever is good enough, yeah, does that mean we don't have to worry about the 0.1% introduced by hardware failures? And that's my provocative question to Florian.
Right. Actually, Simon, I was about to ask you a very similar question after you talk, but I didn't manage to. Yeah, I think today the challenges have been addressed very well. It's probably with the current components, it doesn't look like they're going to be there anytime soon, but that's also part of the way it's measured, as you pointed out, the metrics, the way that we have to patch here and there to overcome all the individual issues. So, and since you have explained very well before this holistic thinking, I could imagine that an interesting idea would be to actually train an AI agent that does the whole pipeline, right? That doesn't do perception, and another one who does the driving, and maybe another one who, I don't know, whatever is left. So maybe we need an AI component who is perceiving and actuating and doing everything at the same time. You train it all at once, and then I think automatically some of the semantic gaps might be closed. But of course, this is immense complexity that we don't have yet. But let's see.
It's a very interesting perspective because typically as a safety engineer, you know, I balk at end-to-end learning because it's the black box is just getting bigger and bigger. However, due to the nature of the way some of these algorithms work, actually that might be the way to compensate for some of the fragility in the system in the individual tasks. So it's certainly an interesting thought to have. Yeah,
exactly.
And I fully agree with this. I cannot agree more, because indeed, if you take individual as a task, then, for example, in the requirements definition, you may wonder for a long time whether some data represent really what your semantic of the task requires. So, for example, a pedestrian. What is a pedestrian? If you only see the feet on a street, is this enough to say it's a pedestrian and to make the detection? But indeed, if you make a full assessment and a full training with the whole data and the whole tasks around it, you can both increase the risks of failure, but also increase the chances of better coupling the different tasks. So as a philosophy, I agree, but bringing it to practice, it's another thing.
John, I think you've been raising your hand for a while.
Yeah, sure. I partly wanted to react to what Simon said, but also a question for Beatrice. So, Simon, I mean, you and I need to solve this problem, of course, but actually the answer is architecture, and the problem is confusing, or potential problem is confusing accuracy on single frames, single images from the overall safety we can get from an architecture. But that takes us back to doing this holistic thing, but almost still holistic. Beatrice, you talked about robustness. One of the things we normally worry about in safety is no single point of failure to hazard. And I was interested in whether or not you make some association between robustness and no single point of failure to hazard, because I personally think they are correlated. Very interested in your thoughts on that.
Yeah, they are correlated, but actually, I am not sure we need to request. I mean, depends at which level you look at the system, at the requirements. So no point of failure is at the system level. While if we talk about the machine learning, we should not request this, because indeed we shall never reach such a thing. So I think, it depends where you set the requirement and how you mitigate this. It's I don't see a real problem in continuing to do aeronautic systems if it was possible before. Actually, what AI brought is just better performance at the item level. So it should only cope better. For the moment, we are not expecting to do absolutely everything. So if you look at the small system level, you can ensure, as before, the system level requirements. So I think it's okay.
Okay, interesting. Maybe we should discuss some other time. I think it actually gets rather more tricky, because you have an algorithm that is susceptible to a change in a single input feature and produces a plausible but wrong output. You may not be able to detect that elsewhere in the system. So I actually think some of the issues of algorithm robustness do directly relate to no single point of failure to hazard. And I don't have a solution, but I do have a worry about that, which is why I raised it.
This was also the case before machine learning, before data.
Yes.
So I mean, it's not a new issue.
Agreed. Yeah, I agree. It's not new, but we do need to solve it in this new world. Anyway, Mauricio, I'll shut up and hand back to you as chairman.
Yep. Okay. I think Huáscar, you're getting ready, right, for the next